Hello, today we're looking at types of collisions. In physics, we have two types of collisions. We have what are called elastic and inelastic collisions. Elastic collisions are those collisions in which the total kinetic energy of a system is conserved or remains the same. So we add the kinetic energy of the system before the collision occurred. So this is before. And then the total kinetic energy after that collision has occurred. So if a collision is elastic, then those two kinetic energies, the sum of those kinetic energies must be the same before and after the collision. So how do we calculate the sum of the kinetic energies before the collision occurred? So this is how we calculate, how we sum up the kinetic energy before the collision occurs. You just say half mv squared, half of the mass times the velocity squared of the first object, and half of the mass times the velocity squared of the second object. Then you add the two together. So this is before the collision. And then this is after the collision has occurred. You also do the same thing. You sum up the kinetic energies of object 1 and object 2 after the collision. And then you compare these two values. If you see that they are equal, then it means that that particular collision is elastic. Alright. In inelastic collisions, the total kinetic energy of the system is not conserved. In other words, it's not the same. Right? So you simply follow the same process here. You look for the kinetic energy before the collision, the kinetic energy after the collision. If you see that the two values are not equal, then you can conclude and say that particular collision was inelastic. So in inelastic collisions, energy is lost in the form of sound, heat, and light energy and other forms. So in nature, most collisions are inelastic because when a collision occurs, you can hear the sound. Yeah, you can see some fire there and things like that. So all that is kinetic energy that has been converted to other forms. However, in both types of collisions, the total linear momentum is always conserved. So this is one very important point. Our linear momentum is always conserved whether the collision is inelastic or it's elastic. Right now, let's look at a question. In this question here, we're told that a boy on roller skate moves to the right at a constant velocity. The joint mass of the boy and the roller skate is 50 kgs. He catches a ball with a mass of 0.4 kgs that is traveling horizontally to the left at a velocity of 6 meters per second. After the boy catches the ball, they both move to the right at a velocity of 1.49 meters per second. Okay, so we're given the before the collision has occurred here, and then this is after the collision has occurred. Alright, the boy is moving to the right with a particular velocity, we are not told. Alright, and he collides with the ball which is moving in the opposite direction. Okay, and after collision occurred, both the ball and the boy move together as a single unit to the right at a velocity of 1.549 meters per second. Right, okay, cool. The first question says define the term impulse. And I hope you still remember how to define the term impulse. It is the product of the net force and the time for which the net force acts on the object. The second question says calculate the magnitude of the average force that the boy exerts on the ball when he catches it. If he and the ball exert a force for a period of 0.1 second on each other. Okay, that's a beautiful question. All right, so for 3.2, we want the magnitude of the net force here. So we're still dealing with vectors, so we still need to choose a positive direction. So let's take let's take right as positive. All right, now we want to find the average force that they're going to exert on each other. So when the boy collides with the ball here, the ball is going to exert a force on the boy, and then at the same time the boy also exerts a force on the ball. These two forces are equal in magnitude but opposite in direction. So what we can simply do is, the question is focusing on the force that the boy exerts on the ball, but it is also the same force that the ball exerts on the boy. So we can simply try to find the force that the ball exerts on the boy, and the force that the boy exerts on the ball will be in the opposite direction. So let's try to find the force that the ball exerts on the boy. So we're going to say F net times the delta t. This is equal to delta p. So F net multiplied by 0.1 equals to mass multiplied by the final velocity minus the initial velocity. So 0.1 F net is equal to the mass of the ball, which was 0.4 kgs, multiplied by the final velocity. We're taking right as positive, so this is positive right here. So it's 1.49 minus the velocity, initial velocity of the ball was to the left, so it's negative, so say negative 6. So we have 0.1 F net is equal to, right, so let's do the calculation there. We have 0.4 multiplied by 1.49 minus 6. Right, so we get 2.996. So then divide both sides by 0.1 here to get our F net over 0.1. It means our F net is equal to, so let's say that answer divided by 0.1. We get 29, yeah, 29.96 newtons. So this particular force is the force of the ball on the boy, right, which is the same thing as the force of the boy on the ball. So there we have the force, right. The second question, the following question here is saying write down the principle of conservation of momentum. I hope you remember to state the principle of conservation of linear momentum. It says the total linear momentum of an isolated system remains the same. Now calculate the velocity, magnitude of the velocity v of the boy before he catches the ball. So initially here we have two objects that were separate, right? So 3.4, we're still taking right as positive. All right, very important to write this statement because you're dealing with vectors. All right, so I'll say mass number 1 times velocity number 1 initial plus mass number 2 times velocity 2 initial equals to mass 1 plus mass 2 multiplied by the final velocity. So I have 50 multiplied by v plus 0.4 multiplied by negative 6. This is equal to 50 plus 0.4 multiplied by 1.49. Right, so 50v minus, so let's do the calculation there, 0.4 times negative 6, so negative 2.4. Right, and then on the right hand side I have 50.4 times 1.49 I get 75.096. I transpose the 50V is equal to, I must get 7.496, as I'm going to add there. Alright, so I then divide both sides by 50. Therefore, our V is going to be equal to, right, so I add this, let me just add 2.4. Alright, then I divide this by 50. So I get 1.54992 meters per second. So that's to the right. Okay, which is equal to 1.55 meters per second to 2 decimal places, right? Okay. Alright, so there I have my initial velocity of the boy. Next up, we have to prove, question says, prove with the necessary calculation that this collision was inelastic. Right, so they are telling us that it was inelastic. So that's 3.5. So we'll say, okay, before collision, right, the sum of the EK initial is equal to 1 over 2 m1 v1 squared plus that's half m2 v2 initial squared. So this is the initial velocity, which is equal to 1 over 2, the mass of the boy is 50 and his velocity was 1.5499 squared plus 1 over 2, the mass of the ball 0.4 times the initial velocity, which is -6 squared, right? Yep. This is equal to, so you then do the calculation. So I have half right there. So I have 67 point, right, so that's 67.2547 joules, which is equal to 67.25 joules, right? So this is the initial sum of the kinetic energies, right? And then I have to look for after the collision has occurred. So I'll say after collision, right? So say the sum of the EK final is going to be equal to 1 over 2 mv squared. So now they're moving as a single unit, so I need to add the masses. So the combined mass is 50.4 multiplied by the final velocity, which is just 1.49 squared. All right, let's see. So I have 1 over 2 multiplied by 0.4 times 1.49 squared. Okay, that gives me 55.947 joules, which is equal to 55.95 joules to 2 decimal places. So now I need to compare these two. Now you can see that they are not the same. We have lost some kinetic energy here, so you can simply conclude and say the sum of the EK initial is not equal to the sum of the EK final. Therefore, collision was inelastic. And then we're done. Alright, so pretty cool. So this is how you prove whether a collision is elastic or inelastic.